If I was a rapper, my name would be Two Tails, but I digress. In this video, we'll be talking about a two-tailed test of significance. Now, there's only a few differences in a two-tailed test, is what we've already been talking about. So on this next slide, I'll talk about those differences. In the question, there will be no direction specified for the alternate hypothesis H sub A. We'll often use keywords like differs or different. Sometimes they'll even say not equal to. Are there any changes? So they're not going to give you a specific less than or greater than, and then you would just use not equal to. So the next difference is in your symbols when you are doing your your alternate hypothesis, you're going to use the not equal symbol instead of less than or greater than. Because you're doing technically the probability of it being less than and greater than, you're going to shade both sides, hence the name two tails. At the very end, mathematically, the only real difference is that you double the p-value. Okay, so let's walk through an example. The medical director of a large company is concerned about the effects of stress on the company's younger executives. According to the NCHS, the mean systolic blood pressure for males 35 to 44 years of age is 128, and the standard deviation of this population is 15. The medical director examines the medical records of 72 male execs in this age group and finds X bar to be 129.93. Is this evidence that the mean blood pressure for young male execs is different than the national average? So, first key word, different. It doesn't say less than or greater than. So I'm actually going to do both directions. Okay, we start off by identifying what type of test. Now, since the population standard deviation is 15, that's sigma, this is a one sample z-test. Okay, so we first kind of want to have an idea of what type of test we're going to conduct. All right, we run through hypotheses. Okay, continued practice on that. The null hypothesis, H sub 0, no change. It's always going to be mu equals for mean problems. Now, if I go back up here in the problem, it says the mean systolic blood pressure is 128. The alternate hypothesis, mu 128. Notice that I write those two things automatically because I know they're going to be the same. I'm going back to different, so I'm going to say not equal to. And of course, I'm going to identify my parameter that mu is the mean systolic blood pressure for younger executives. Okay, or younger male executives. All right. Now we move to the conditions, everyone's favorite part. For the sake of the time in this video, we're just going to kind of skip over this. I guess, of course, you would do this in a problem. The conditions are all met. I'll briefly discuss them. We're going to assume that this is a random sample. It doesn't say it in the problem, so we would write assume the sample is random or results may be biased. 72 is my n. That's definitely over 30. Central limit theorem applies. And the independence, we can assume that the 10 times the sample is less than the population. So we're going to move right on to my favorite part, the calculations. Okay, again, we are conducting a one sample z-test. So z equals x bar minus mu over sigma sub x bar. We identify our formula first. All right, we're going to draw our graph, label the middle, all right, which is 128. That's our mu, or what we think the mean blood pressure is. From our sample, we got an x bar of 129.93, which is above 129.93, and we're going to shade to the right. Now we're going to double that and shade to the left as well because it is a two-tailed test. That's mean, that's my x bar. Okay, standard deviation of x bar, I'm going to recalculate. It is 15, which again, I got from the problem. All right, divided by the square root of 72, which is going to give me 1.77. Okay, so I'm going to plug these numbers in to my z-score to get the test statistic. 129.93 minus 128 over 1.77, which is going to give me a z-score of 1.09. I type that in my calculator, normal CDF. Now, since that's a positive z-score, and I'm going to the right here, I'm going to go 1.09, one and a bunch of zeros, and I'm going to get a p-value of 0.1379, which I'm going to double because it's a two-tailed test, and get an overall p-value of 2757, which right now we know it's very high. So we go to our conclusion. Okay, now it did not specify a alpha. So we're just going to use alpha equals 0.05. So if it doesn't specify, I like to use alpha equals 0.05. All right. Our p-value is clearly above that. So we get to see what it looks like to fail to reject a problem. So our conclusion, we will fail to reject h sub 0 mu equals 128. Since our p-value 0.2757 is greater than 0.05, which is our alpha level. And now we write this in the context. So we've made our decision. We're failing to reject. We've said why, and now we apply the context. Now, I can go up to the problem and usually use the last sentence. Is this evidence, okay, that the mean blood pressure for younger male execs is different from the national average? So we do not have evidence that the mean systolic blood pressure of younger male executives is different from 128. Okay, now notice again we are failing to reject the null hypothesis. We're not accepting it. So in my conclusion, in my context, I'm not saying that the mean blood pressure is 128. I'm not accepting that fact. I'm just not saying that it's different. I know there's some double negatives going on there, and it does get a little bit tricky, but the more we practice this, the better we'll become. So we do not have evidence that the mean blood pressure is different than 128.